Good afternoon, everyone. Get prepared. What do we have today, guys? Okay, guys, let's begin. So, as you know, today we're going to have our last quiz. So, this is the last assessment, guys, before final exam. Okay. So, we will have quiz 2. At what time? Everything is announced on Moodle at very good 01:05 p.m. today. And which section? It's only about section 7.1, what we did on Thursday. So we talked about it. So please, guys, at 1 o'clock, remind me to stop so you can start quiz on time. Okay, guys? Okay. No, there is no statement. Only true, false, multiple choice. That's it. As we did in quiz 1. You forget quiz 1, Nora? Okay, same structure. Now please click on yes for present. Okay. So our presentation. So we are done with section 7.1. You can see the presentation, guys. Okay. So what we did before, we have seen how to find eigenvalues, eigenvectors, right? So in section 7.1, we have seen if we have a square matrix n by n, we have seen how to find characteristic polynomial occurring. So characteristic polynomial is p lambda equal to determinant lambda in minus a. We have seen how to find eigenvectors, eigenvalues. How to find eigenvalues? We take p lambda equals 0 and we solve the characteristic equation. This one we call it characteristic equation. And finally, we have eigenvectors. How to find eigenvectors for each lambda. Let's call it lambda I. We solve lambda I in minus AV equals 0. Homogeneous system, and V here, it's A, B, C, D, and something like this. Correct, guys? Okay. Now, let's check 7.2. I prefer directly. I read everything and explain it. Those who comes late, guys, so don't forget today we have quiz 2 at 1:05. Okay, at 5 minutes. It's only about section 7.1. Okay, Khalifa, no problem. Okay. So, what do we have here? So we have section 7.2. This is the last section for this course, guys. It's very important. You will see here, we are going to use again all properties, all the basic notions that we have seen before, determinant, properties of determinant, REF, how to find eigenvalues, eigenvectors. So you see, linear algebra, it's an easy course, but for sure you will use all material. Okay, guys? So you have to remember always how to do determinant, properties for determinant, how to use REF, everything. So Here we are going to talk about similar matrices, so I prefer to erase everything and I explain step by step. So, let's keep this one. Keep the title, no problem for the title. So, diagonalization and similar matrices. So let's talk first about similar matrices. What does mean similar matrices? So, two square matrices, guys. Square matrices A and B. So two square matrices of the same size. So n by n are said to be similar. So we say that two matrices are similar if we can find a non-singular matrix P. What does mean non-singular matrix means? P inverse exists, correct? Means you can find the inverse of this matrix, such that this is the most important, such that A equal to P, B, P minus 1. So you see, B is in the middle between P and P minus 1. Or you can write B equal P minus 1, A, P. So if you can find two matrices, one is equal to another one, which is in the middle between matrix and its inverse, means that these two matrices are similar. And for these two matrices, we have some properties. A, if A and B are similar, what does mean similar? Directly you write A equal to P, B, P minus 1. In this case, then, first property, they have the same eigenvalues. They have the same eigenvalues. Two, determinant of A will be equal to determinant of B. Three, A to the power of n is equal to P, B, n to the power, B to the power of n, P minus 1. This is very important, guys. So in this section, we will see how to find P, how to find B, this matrix which is similar to A, and how to find the power of a matrix if we can write A as P, B, P minus 1. Understood, guys? So definition of similar matrices is very important. If we can write A equal to some matrix multiply the similar one B multiply inverse of that some matrix. So here A is equal to P invertible matrix P B P minus 1. This one means A and B are similar, or like this one. And guys, why determinant of A equal to determinant of B? Too simply because, look, let's check what's the determinant of A. Determinant of A, it's equal to determinant P, B, P minus 1. If we apply properties of determinant, it's equal to, we split it, determinant of P multiply determinant of B multiply determinant of P inverse, correct? Means it's equal to determinant of P multiply determinant of B multiply 1 over determinant of P. Look, determinant of P multiply 1 over determinant of P is equal to 1. So finally we get 1 multiplied determinant of B. So you see determinant of A is equal to determinant of B. So it's easy. Understood, guys? Very good. So if you want, guys, here, so this is proof of this one. You can take screenshots if you want. No. What does mean diagonalization? Please take screenshot because I will start diagonalization. Okay. Now, diagonalization, what does mean A is diagonalizable? So, given again a n by n matrix. Okay, guys? So, if we have n by n matrix, this matrix, we can find eigenvalues. If we have, so look here, n number of rows equal to number of columns. So we have here the number n. If we have exactly n distinct eigenvalues, if we are in this case here, we have n distinct eigenvalues. What does mean distinct? Means they are different from each other. In this case, immediately you say that A is diagonalizable. We say that A is diagonalizable means it's similar to a diagonal matrix. Okay, guys, for that we use this word, diagonalization. Means A is similar to a diagonal matrix. This one is diagonal. So if it's similar to diagonal matrix, we say it's diagonalizable. But when do we know if it's diagonalizable or not? So this is the first case. If you have n distinct eigenvalues, then A is diagonalizable. So if all eigenvalues, first of all, we have how many? We have n, the same n here. It's 3 by 3. We need 3 different from each other. For example, assume A is 3 by 3 matrix. And if I find lambda 1 equal 1, lambda 2 equal 2, lambda 3 equal minus 1, do we have distinct? Do we have all different from each other? In this case, yes, A is diagonalizable directly. This is the easiest case. If we have all eigenvalues are distinct and their number is equal to number of rows or number of columns, then we have A diagonalizable. What is the second case? If we don't have n distinct eigenvalues, if we don't have n distinct eigenvalues, what does mean this one? Means we have less. Maximum n, so we have less than n, okay? But all eigenvectors, now we move to eigenvectors. But all eigenvectors are linearly independent, or if you want, all eigenvectors are form a basis for Rn, because here we have n. So we have vector 1, vector 2, vector n, all form a basis. In this case, again, here, we get also A is diagonalizable. So guys, look, we have 2 cases. If we have exactly n eigenvalues which are all distinct, all different from each other, immediately A is diagonalizable. We finish in two steps. We find eigenvalues, we deduct. We deduce this one. Now, if we don't have n distinct eigenvalues, we don't have this case, it doesn't mean it's not diagonalizable. It can be diagonalizable, it cannot. Okay? We have two cases. Which cases we are sure that A is diagonalizable? If all eigenvectors form a basis. We have to find n eigenvectors. All n eigenvectors form a basis for Rn. If we have less than n, so less than dimension means it's not diagonalizable. Understood, guys? Just a second. Okay. Yes, no. So here, you will understand this from examples. Yeah, for sure, we'll do example. So if we are in this case, we have all eigenvalues are different from each other, directly A is diagonalizable. But if we don't have this case, then we don't say A is not diagonalizable. No, we have two cases. We have to look if from the eigenvalues you don't have any result, means we don't have n distinct eigenvalues, then you have to move to eigenvectors. When you move to eigenvectors, if the eigenvectors form a basis, then it's diagonalizable. If it doesn't form a basis, then it's not diagonalizable. That's it. Now, assume A is diagonalizable. Now we know what's meaning diagonalizable. If A is diagonalizable, then we can write A is similar to a diagonal matrix P, D, P minus 1. How to get D? D is too simply, guys. You put all eigenvalues on the main diagonal. Here 0, here 0. And how to get P? P is too simply, V1 is the eigenvector associated with lambda 1. V2, eigenvector associated with lambda 2. Vn, eigenvector associated with lambda n. Too simply. We put them by order. Eigenvalue, eigenvector associated with lambda 2, eigenvector associated with lambda n. This is how to get P. So P is too simply the matrix of all eigenvectors. If A is diagonalizable, we know that all these vectors are form a basis, means the determinant of this matrix is different from 0, so for that it's invertible. So you see, it's all related. Let's directly hit an example to understand the idea of diagonalizable. So we have the matrix A, 1, 1, minus 2, 4. We want to see if we can find a diagonal matrix similar to A. What does mean this one? A is similar to a diagonal matrix means diagonalizable. We want to check if A is diagonalizable. Means it's similar to a diagonal matrix. If we can write A as P, D, P minus 1. And D is diagonal. So let's check, as we did before. We have to look on the eigenvalues. If all eigenvalues are distinct, we are fine. If they are not distinct, means we have to move to eigenvectors. If the eigenvectors form a basis, means determinant is different from 0, means linearly independent, then it's a basis, means diagonalizable. Here, let's check first. Hopefully, we have eigenvalues are distinct. So we have to find P lambda, which is determinant lambda I2 minus A. So here it will be lambda minus 1, minus 1, 2, lambda minus 4, correct? So multiply lambda minus 1, multiply lambda minus 4, minus 2 multiply minus 1, it's minus 2, so it will become plus 2. So multiply here lambda squared, we open the bracket, minus lambda 4, minus 4 lambda, minus lambda, plus 4, plus 2. So finally we get lambda squared, minus 5 lambda plus 6. Now how to find eigenvalues? We take P lambda, very good, equals 0. So, and here we can do it, mod 5, 3 guys, what do we get? Three and do we have distinct eigenvalue? So, first of all, A is a 2 by 2 matrix. And we have two distinct eigenvalues. You see, different from each other. Distinct eigenvalues. So, immediately, you see, Nora? So, is it diagonalizable? So, A is, yes, it's diagonalizable if they are distinct. Look, you see here, distinct means diagonalizable. You see it? Very good. It's diagonalizable. What does mean this one? Means A is equal to P, D, P minus 1. And how to write this D? D is equal to lambda 1, 0, 0, lambda 2, means lambda 1, 3, 0, 0, 2. So you see, it's similar to a diagonal matrix. This one is diagonal. Always, if it's diagonalizable, means similar to a diagonal matrix. Abdullah, we will do an example, don't worry. Please take screenshot, guys, and we move to another exercise. This one, it will be not diagonalizable, so you will see, Abdullah. So, is it diagonalizable? First of all, we have to check if we have distinct eigenvalues. So let's check P lambda. Lambda I2 minus A. So it will be lambda minus 1, 0, lambda minus 1. What's the determinant of this matrix? You multiply lambda minus 1, multiply lambda minus 1, so it's lambda minus 1 squared, minus 0. So we get lambda minus 1 squared, which is lambda squared minus 2 lambda plus 1. Even we can keep it. Now, eigenvalues, if we have two different eigenvalues, means diagonalizable. If not, we don't know. We have to move to eigenvectors. If we get two linearly independent eigenvectors, means diagonalizable. If not, not diagonalizable. So eigenvalues, let's check. P lambda equals 0. Can you do it, guys? On calculator, what do you get? We get how many eigenvalues? Only one, lambda equal 1. We have only one. Only one eigenvalue. Can we say that it's diagonalizable or not? No, we cannot say anything. So we cannot say that A is not diagonalizable. And we cannot say A is diagonalizable. So what we have to do, Nora, here we have to check eigenvectors. Now you move to eigenvectors. So we have to check if we have two eigenvectors forming a basis. What does mean forming a basis means? They are linearly independent, because if K equal N, remember this one? That linearly independent is equal to basis. So here, let's check if we have two linearly independent eigenvectors. Why 2 in R2? Because here it's 2 by 2. To have a basis of R2, we need 2, right? Okay, let's check. So, we have only for lambda equal 1, we solve lambda I2, here we call it lambda the same, I2 minus A, or let's call it lambda 1 only, we have only one lambda. Lambda 1 I2 A V equals 0. And this V here, it's equal to AB or ABC? Very good, AB. Very good. Now, let's move to augmented matrix. What's the augmented matrix? Instead of lambda, put 1, so we get 0, negative 1, 0, 0, and here 0, 0. R1 divided by minus 1. Very good, guys. 0, 1, and all zeros. So, don't forget, here we have A and B. I have leading 1 for B. I don't have leading 1 for, so A is free, very good. And B, yeah, it's free variable, and B equals 0, very good. So let's write B, V, which is AB, substitute A is free, we keep it, B, 0. And we can take any A different than 0, A different than 0, right? So we take A equal 1, very good, different than 0. So we get V1 equal 1, 0. So look, you see, an eigenvector, we have only one eigenvector associated with lambda. So conclusion, guys, is it this one? Is this a basis for R2? To have a basis for R2, how many vectors do we need? We need two linearly independent eigenvectors. Since we have only one vector in R2, so it does not form a basis for R2. So since we don't have bases, eigenvalue vectors don't give us a basis, so immediately what do we say? So A is not diagonalizable. So we have only one vector. We need two linearly independent. Here we have only one. It's impossible to have a basis for R2. It's not a basis. Only with one vector, it's not basis for R2. Why? Because dimension of R2 is 2. Means we need two vectors, right? To have a basis. No problem, Nora. You understand that, Nora? Very good. So please take a screenshot. And guys, prepare for the quiz. So we will start quiz after 15 minutes. We will stop here because we continue on Thursday, guys. Yes, absolutely. It's almost all. Yes, correct. So please, guys, take a screenshot if you want and get prepared. We start quiz in 15 minutes, right? Okay. So you can revise if you want, and so we discuss at 1:05. So guys, don't forget, we will do quiz at 1:05. It's written in front of you.